Jupyter in JUnit. Now we are focusing on Jupyter. JUnit Jupyter is the combination of the new programming model and extension model for writing tests and extensions in JUnit 5. The Jupyter subproject provides a test engine for running Jupyter-based tests on the platform. Here in dependency diagram, you can see org.junit.jupyter package, and you can see here JUnit Jupyter engine and JUnit Jupyter migration support, JUnit Jupyter params, and this is JUnit Jupyter, and here JUnit Jupyter API. Here you can see per method lifecycle. With regarding lifecycle methods, a lifecycle method is any method that is annotated with before all, after all, before each, and or after each annotation. The lifecycle methods execute before or after executing the actual test methods. Before all and after all annotations denote that the annotated method should be executed before or after all test methods in the test class. If you have 10 test methods in the test class, before each and after each will be executed 10 times, but before each and after each here, but before all and after all only once. Here you can see a per method lifecycle. In per method lifecycle, this is a test instance lifecycle here. By default, JUnit creates a new instance of the test class before executing each test. Each test method. This helps us to run individual test methods in isolation and avoid unexpected side effects. Here this before all and after all are static methods normally. This is because when creating a new test instance per test method, there is no shared state otherwise. When you're looking at the output, we can see that JUnit construct the test class once per each test. Each test method. The lifecycle methods for entire fixture have been executed once, and the lifecycle methods for tests have been executed multiple times. Here the annotation interface before all. Ampersand before all is used to signal that the annotated method should be executed before all tests in the current test class. In contrast to ampersand before each methods, before all methods are only executed once for a given test class. Annotation interface before each. Ampersand before each is used to signal that the annotated method should be executed before each ampersand test or repeated test or ampersand parameterized test or ampersand test factory and ampersand test template method in the current test class. Annotation interface after each. ampersand after each is used to signal that the annotated method should be executed after each ampersand test, ampersand repeated test, ampersand parameterized test, ampersand test factory, and ampersand test template method in the current test class. Annotation interface after all. Ampersand after all is used to signal that the annotated method should be executed after all tests in the current test class. In contrast to ampersand after each methods, after all methods are only executed once for a given test class. Here, before all is connected to constructor test class instance, and constructor test class instance is connected to before each, ampersand before each, and ampersand before each is connected to execute test. Execute test is connected to ampersand after each. Ampersand after is connected to construct a test class instance. Next test is passed from after each to constructor test class instance. After each, ampersand after is connected to ampersand after all test done is passed from ampersand after each to ampersand after all. Here you can see test see a per class lifecycle or test instance per class. It is also possible to make JUnit execute all test method in the same test instance. If we annotate the test class with ampersand test instance lifecycle.per class, JUnit will create a new test instance once per test class. So because of the shared instance, there is now no need for the method to be static. From the execution results, we can see that the execution order of the lifecycle methods has not changed. However, the difference is that JUnit constructs the test class only once. The fundamental difference is that the default lifecycle method constructing a new test class instance resets the state stored in the instance variable, when per class lifecycle method construct the instance only once. State stored in instance variable is shared between tests. If your test methods rely on state stored in instance variable, you may need to reset the state in before each and or after each lifecycle methods. Try to avoid writing tests that rely on state stored in instance variables. Here you can see the construct test class instance is connected to ampersand before all, and before all is connected to before each, and before each is connected to execute test, and execute test is connected to after each. After is connected to before each, and new test is passed from after each to before each, and after is connected to after all, and all test done is passed from after each to after all. Here you can see extension lifecycle. JUnit 5 Jupyter provides extension authors callbacks that can be used to tap into the lifecycle events of tests. The extension model provides several interfaces for extending test at various points in the extension lifecycle. Extension authors are free to implement all or some of these lifecycle interfaces. Interface before all callback. Before all callback defines the API for extensions that wish to provide additional behavior to test containers once before all tests in the container have been executed. Interface before each callback. Before each callback defines the API for extensions that wish to provide additional behavior to test before an individual test and any user-defined setup methods. For example, ampersand before each methods. For that, the tests have been executed. Interface before test execution callback. Before test execution callback defines the API for extensions that wish to provide additional behavior to test immediately before an individual test is executed, but after any user-defined setup methods. For example, ampersand before each methods have been executed for that test. Interface after test execution callback. After test execution callback defines the API for extensions that wish to provide additional behavior to test immediately after an individual test has been executed, but before any user-defined teardown methods. For example, ampersand after each methods have been executed for that tests. Interface after each callback. After each callback defines the API for extensions that wish to provide additional behavior to tests after an individual test and any user-defined teardown methods. Ampersand after each methods for that test have been executed. Interface after all callback. After all callbacks defines the API for extensions that wish to provide additional behavior to test containers once after all tests in the container has been executed. Here you can see the lifecycle callbacks here. Before all callback is connected to before each callbacks, and before each callbacks is connected to before test execution callback. Before test execution callback is connected to after test execution callback. After test execution callback is connected to after each callback. After each callback is connected to after all callback. Here you can see the JUnit 5 architecture, basically considering JUnit Jupyter. One could think that JUnit 5 is solely a testing framework, and that while this is theoretically right, JUnit is actually composed of 3 modules: JUnit Platform, JUnit Jupyter, and JUnit Vintage. JUnit Platform, the platform module is essential module that runs the test on JVM. The JUnit Jupyter, the Jupyter module provides programmers a new combination of the programming model and execution for writing test on JUnit 5. JUnit Vintage, the Vintage module allows running tests from older versions, the JUnit 3 and JUnit 4 on the platform. Here you can see as an example is connected to JUnit Jupyter. Here JUnit Jupyter is connected to JUnit Jupyter Param, JUnit Jupyter API, JUnit Jupyter Engine, and JUnit Jupyter Param is connected to JUnit Jupyter API, and JUnit Jupyter Engine is connected to JUnit Jupyter API. JUnit Jupyter Param is connected to API Guardian API. And here JUnit Jupyter API is connected to API Guardian API, JUnit Platform Commons, and open test 4j. Here JUnit Jupyter engine is connected to API Guardian API and JUnit platform engine. Here the JUnit platform engine is connected to API Guardian API and JUnit platform commands and open test 4j, and here JUnit platform commands is connected to API Guardian API. Here the JUnit Jupyter aggregates artifact that transitively pulls in dependencies on JUnit Jupyter API, JUnit Jupyter params, and JUnit Jupyter engine for simplified dependency management on inbuilt tools such as Gradle and Maven. JUnit Jupyter API, JUnit Jupyter API for writing tests and extensions. JUnit Jupyter params supports for parameterized test in JUnit Jupyter. JUnit Jupyter engine, JUnit Jupyter test engine implementation only required at runtime. Here the this is published in at API Guardian jar, and in addition, here the most of the artifacts have a direct and transitive dependency on the following open test 4j jar. JUnit platform commands, common APIs and support utilities for JUnit platform. Any API annotated with at API status equal internally is intended to solely for usage within the JUnit framework itself. Any usage of internal APIs by external parties are not supported. JUnit platform engine, public APIs for test engines. As an example, we can consider JUnit Jupyter params. The artifact ID JUnit Jupyter params support for parameterized tests in JUnit Jupyter. This is in the group ID org.junit.jupyter. As an example 2, we can consider this code segment. Following example demonstrates a parameterized test that uses ampersand value source annotation to specify a string array as the source of arguments. Annotation interface parameterized test. Ampersand parameterized test is used to signal that the annotated method is parameterized test method. Such methods must not be private or static. Parameterized tests make it possible to run a test multiple times with different arguments. They are declared just like a regular ampersand test method, but use ampersand parameterized test, annotation instead. In addition, you must declare at least one source that will provide the argument for each invocation, and then consume the arguments in the test method. When executing this parameterized test method, each invocation will be reported separately. For instance, the console launcher will print output similar to the following here. As an example 3, we can consider JUnit artifact ID JUnit-Jupyter-migration support. Support for migrating from JUnit 4 to JUnit Jupyter, only required for support for JUnit 4's &igno annotation and for running selected JUnit 4 rules. This is in group ID org.junit.jupyter. Here, as an example 4, we can consider this code segment. Annotation interface enable JUnit 4 migration support. Enable JUnit 4 migration support is a class level annotation that enables all JUnit 4 migration support within JUnit Jupyter. Specifically, this annotation registers all extensions supported by enable rule management, rule migration support, and provides support for JUnit's force &igno annotation for disabling test classes and test methods. Technically speaking, enable JUnit for migration support is a composed annotation which registers all of the following migration extensions: verifier support, external resource support, expected exception support, and ignore condition. Note, however, that you can optionally register one or more of these extensions explicitly without the use of this composed annotation. And this is in module org.junit.jupyter.migration support, and in the package org.junit.jupyter.migration support. In order to provide the smooth migration path from JUnit 4 to JUnit Jupyter, the JUnit-Jupyter migration support module provides support for JUnit 4's igno annotation analogous to Jupyter's disabled annotation. To use igno with JUnit Jupyter-based test, configure a test dependency on the JUnit-Jupyter-migration support module in your build, and then annotate your test class with extent with ignore condition.class, or enable JUnit for migration support, which automatically registers the ignore condition along with limited JUnit for rule support. The ignore condition is an execution condition that disable test class or test methods that are annotated with ignore. As an example 5, we can consider this Gradle segment. To configure support for JUnit Jupyter-based test, configure a test implementation dependency on the dependency aggregating JUnit Jupyter artifact similar to the following here, and here you can see the group id org.junit.jupyter, JUnit Jupyter here. As an example 6, we can consider this one, the Maven segment here. To configure the support for JUnit Jupyter based tests, configure test scoped dependencies on the JUnit Jupyter API and the JUnit Jupyter test engine. Implementation similar to following here. You can see the here group id org.junit.jupyter, JUnit Jupyter here. Here, as an example 7, we can consider per method lifecycle here in this code segment. A lifecycle method is we're considering lifecycle methods also. A lifecycle method is any method that is annotated with sign before all, I'm saying before after all, I'm saying before each, I'm saying after each annotation. Lifecycle methods execute before or after executing the actual test methods. The ampersand before all and ampersand after all annotations denote that the annotated method should be executed before or after all test methods in the test class. Respectively, ampersand before each and ampersand after each means that annotated method should be executed before and after each test method in the test class. If you have 10 methods, 10 test methods in the test class, before each and after each will be executed 10 times, but before all and after all only once. By default, JUnit creates an here per method lifecycle. By default, JUnit creates a new instance of the test class before executing each test. This helps us to run individual test methods in isolation and avoids unexpected side effects. Notice how the methods annotated with ampersand before all, ampersand after all are static methods. This is because when creating a new test instance per test method, there is no shared state otherwise. Executing the test in the test class gives us the following output. Actually, the output has been formatted to make it more obvious. Looking at the output, we can see that JUnit constructs the test class once per each test. Test method, the lifecycle method for an entire fixture has been executed once. And the lifecycle method for test have been executed multiple times. Here, annotation interface before all. Ampersand before all is used to signal that the annotated method should be executed before all tests in the current test class. In contrast to ampersand before each methods, ampersand before all methods are only executed once for a given test class. Annotation interface after all. Ampersand after all is used to signal that the annotated method should be executed after all tests in the current test class. In contrast to ampersand after each methods, after all methods are only executed once for a given test class. Annotation interface before each. Ampersand before each is used to signal that the annotated method should be executed before each ampersand test, repeated test, ampersand parameterized test, ampersand factory, and ampersand test template methods in the current test class. Annotation interface after each is used to signal that the annotated method should be executed after each ampersand test, repeated test, ampersand parameterized test, ampersand test factory, and ampersand test template method in the current test class. Here the ampersand test is used to signal that annotated method is a test method, and ampersand test methods must not be private or static and must not return a value. Ampersand test method may optionally declare parameters to be resolved by parameter solvers, and ampersand test may also be used as a meta annotation in order to create custom composed annotation that inherits the semantics of ampersand test. Per class lifecycle, it is also possible to make JUnit to execute all test methods on the same test instance. If we annotate the test class with ampersand and its test instance lifecycle.per_class, JUnit will create a new test instance once per test class. Because of the shared instance, there's now no need for the methods to be static static. Consequently, output of the test execution is now a little different. From the result, we can see that the execution order of lifecycle methods has not changed. However, The difference is that the JUnit construct a test class only once. The fundamental difference is that the default lifecycle method constructing a new test class instance and reset the state stored in the instance variable. When the per class lifecycle method construct the instance only once, state stored in the instance variables is shared between tests. If your test methods rely on the state stored in instance variable, you may need to reset the state in ampersand before each and ampersand after each lifecycle methods. Try to avoid writing tests that rely on state stored in instance variables. Extension lifecycle. When using extensions, JUnit calls extension lifecycle callbacks in addition to lifecycle methods in the test class. JUnit guarantees wrapping behavior for multiple registered extensions. Given extension 1 and extension 2, it is guaranteed the before callbacks of extension 1 execute before extension 2. Similarly, it's guaranteed by after callbacks of extension 1 execute after extension 2. Executing the example here, we can see the wrapping behavior of the extensions. Interface before each callback. Before each callback defines the API for extensions that wish to provide additional behavior to test before an individual test, and any user design setup methods for example, before before each methods for that test have been executed. Concrete implementation often implement after each callback as well, if you do not wish to have your callback wrapped around user-defined setup and teardown methods implement before test execution callback and after test execution callback, instead of before each callback and after each callback. Here you can see the method void before each extension context, and this callback that is invoked before an individual test, and any user-defined setup methods for that test have been executed. Interface after each callback. After each callback defines API for extensions that wish to provide additional behavior to test after an individual tests, and any user-defined teardown methods, for example, after each for that test have been executed. Concrete implementation often implement before callback as well. If you do not wish to have your callback wrapped around user-defined setup and teardown method, implement before test execution callback and after test execution callback instead of before each callback and after each callback. Method void after each extension context, callback that is invoked after an individual test, and any user-defined teardown methods for that the test have been executed. Here annotation interface extend with. Ampersand extend with is a repeatable annotation that is used for to register extension for the annotated test class, test interface, test method, parameter field. Annotated parameters are supported in test class constructed in test methods and in ampersand before all, ampersand after all, ampersand before each, ampersand after each cycle methods. Ampersand extend with fields may be either static or non-static. As an example 10, we are considering module org.junit.jupyter aggregates all JUnit Jupyter modules. Here JUnit Jupyter in dependency metadata, the group ID org.junit.jupyter. Here the artifact ID JUnit Jupyter aggregate artifact that transitively pulls in dependencies on JUnit Jupyter API, JUnit Jupyter params, and JUnit Jupyter Engine for simplified dependency management in built tools such as Gradle and Maven. JUnit Jupyter API, the JUnit Jupyter API for writing test and extensions. JUnit Jupyter Engine, JUnit Jupyter test engine implementation only required at runtime. JUnit Jupyter params, support for parameterized tests in JUnit Jupyter. JUnit Jupyter migration support for migrating from JUnit 4 to JUnit Jupyter, only required for support for JUnit 4's @ignore annotation and for running selected JUnit 4 rules. As an error example, we can consider this one. Ampersand parameter 0 is used more than once, and java.line.exception parameter is used more than once at org.junit.runners.parameterize.block JUnit 4 test class runner with parameters.valid text field. Now we are focusing on JUnit Jupyter API. JUnit Jupyter API for writing tests and extensions. Here you can see the sequential workflow of the lifecycle annotations for JUnit 5 is as follows. The method 1, the method annotated with at before all is executed once at the start of the class. To the method annotated with the before each is executes before test case 1 begins. 3, the method test case 1 annotated with at test is the test case in the class. The method annotated with at after each runs after the test case 1 complete execution. 5, the method annotated with before each at before each execute before the test case 2 begins. 6, the method test case 2 annotated with that test is the test case in the class. 7, the method annotated with that after each runs after the test case 2 complete execution. 8, the method annotated with at after all is executed once at the end of the class after both test case 1 and test case 2 are executed. Here the annotation interface before all in package org.junit.api in module org.junit.api. At before all is used to signal that the annotated method should be executed before all test in the current test class. Annotation interface before each. At before each is used to signal that the annotated method should be executed before each at test at repeat test at parameter state at test factory and at test template method in the current test class. The annotation interface test at test is used to signal that the annotated method is the test method. Annotation interface after each. At after each is used to signal that the annotated method should be executed after each at test. At repeat test, at parameters test, at test factory and at test template method in the current test class. Annotation interface after all. At after all is used to signal that the annotated method should be executed after all tests in the current test class. Here the at before each before all is connected to at before each, and at before each connected to at test case 1. It is connected to at after each, and then at after is connected to at before each, and at before each is connected to at test case 2, and it is connected to at after each, and at after each is connected to at after all. Here you can see the relative execution order of the user code and extension code. This diagram illustrates the relative order of user supplied code. And the extension code. User supplied test and the lifecycle method are shown in orange, with callback code implemented by extensions shown in blue. The gray box denotes the execution of a single test method and will be repeated for every test method in the test class. Here the step 1, the interface or annotation. The interface org.junit.jupyter.api.extension.before all callback. Extension code executed before all tests of the container are executed. To the annotation org.junit.jupyter.api.before all user code executed before all tests of the container are executed. Interface 3, the interface org.jupyter.api.extension.lifecycle method execution exception handler handler before all method execution exception. Extension for handling exception thrown from at before all methods. For interface org.junit.jupyter.api.extension.before each callback. Extension code executed before each test is executed. File the annotation org.junit.jupyter.api.before each user code executed before each test is executed. The 6, the interface org.junit.jupyter.api.extension.lifecycle method execution exception handler handler before each method execution exception. Extension code for handling exception thrown from the before each methods. 7, interface org.junit.jupyter.api.extension.before test execution callback. Extension code executed immediately before a test is executed. 8, annotation org.junit.jupyter.api.test user code of the actual test method. 9, interface org.junit.jupyter.api.extension.test execution exception handler. Extension code for handling exception thrown during a test. 10, interface org.junit.jupyter.api.extension.after test execution callback. Extension code executed immediately after a test execution and its corresponding exception handlers. 11, annotation org.junit.jupyter.api.after each user code executed after each test is executed. 12, interface org.junit.jupyter.api.extension.lifecycle method execution exception handler handle after each method execution exception. Extension code for handling exception thrown from at after each methods. 13, interface org.junit.jupyter.api.extension.after each callback. Extension code executed after each test is executed. 13, 14, annotation org.junit.jupyter.api.after all user code executed after all tests of the container are executed. 15 interface org.junit.jupyter.api.extension.lifecycle method execution exception handler hash handle after all method execution exception. Extension code for handling exception thrown from the after all methods. Interface org.junit.jupyter.api.extension.after all callback. Extension code executed after all tests of the container are executed. In the simplest case, only the actual test method will be executed. Step 8. All other steps are optional depending on the presence of user code or extension support for corresponding lifecycle callbacks. For further details on the various lifecycle callbacks, please consult the respective Java doc for each annotation and extension. Here the interface before all callback in package org.junit.jupyter.api.extension in module org.junit.jupyter.api. This before all callback defines and the API extension that wish to provide additional behavior to test containers once before all tests in the container have been executed. The annotation interface before all in package org.junit.jupyter.api in module org.junit.jupyter.api. At before all is used to signal that annotated method should be executed before all tests in the current test class. The here the default void handle before all method execution exception extension context throwable in the interface lifecycle method execution exception handler. Handle the supplied throwable that was thrown during the execution of at before lifecycle method. Interface before each callback. Before each callback defines the API for extensions that wish to provide additional behavior to tests before an individual test and any user-defined setup method, for example before each methods for that the test have been executed. Annotation interface before each. At before each is used to signal that the annotated method should be executed before each at test, at repeated test, at parameterized test, at test factory, and at test template method in the current test class. Default void handle before each method execution exception extension context throwable in interface lifecycle method execution exception handler. The handle the supply throwable that was thrown during the execution of before each lifecycle method. Interface before test execution callback. Before test execution callbacks defines the API for extension that wish to provide additional behavior to the test immediately before an individual test is executed. But after any user-defined setup method, for example, at before each methods have been executed for that test. Annotation interface test. A test is used to signal that annotated method is a test method. Interface test execution exception handler. The test execution exception handler defines the API for extensions that wish to handle exceptions thrown during the test execution. Interface after test execution callback. After test execution callbacks define the API for extensions that wish to provide additional behavior to test immediately after an individual test has been executed before any user-defined tear-down methods. For example, after each methods have been executed for that test. Annotation interface after each. After each is used to signal that the annotated method should be executed after each at test, at repeated test, at parameterized test, at test factory, and at test template method in the current test class. Handle after each method execution exception. The default void handle after each method execution exception. Extension context throwable. In interface lifecycle method execution execution exception handle the supply throwable that was thrown during the execution of after each lifecycle method. Interface after each callback. After each callback, define the API for extensions that want to provide that wish to provide additional behavior to test after an individual test, and any user-defined tear down methods. For example, at after each method that the test have been executed. The annotation interface after all. At after all methods must have a void return. The after all is used to signal that the annotated method should be executed after all tests in the current test class. The default void handle after all method execution exception, extension context throwable in interface lifecycle method execution exception handle the supply throwable that was thrown during the execution of at after all lifecycle method. Interface after all callback. After all callback define the API for extensions that wish to provide additional behavior to test containers once after all tests container have been executed. Here the extension codes are here, the before all callback, before and these exceptions, and before each callback, before test execution callback, after test execution callback, after each callback, after all callback, and these lifecycle methods. And the user codes are at before all, at before each, at test, at after each, at after all. Here the steps, the order is before all callback, then at before all to the lifecycle method execution exception handler at hash handle before all method execution exception, then before each callback, then at before each, then lifecycle method execution exception handler at hash handler before each method execution exception, then before test execution callback, then at test, then test execution exception handler, then after test execution callback, then at after each, then lifecycle method execution exception handler hash handle after each method execution exception, then at after each callback, then at after all, then lifecycle method execution exception handler hash handle after all method execution exception, then after all callback. Example, we can consider the module org.junit.jupyter.api defines JUnit Jupyter API for writing tests. As an example 2, we can consider this code segment writing tests. The following example provide a glimpse at the minimum requirement for writing a test in JUnit Jupyter. Annotation interface test. Ampersand test is used to signal that the annotated method is a test method. Annotation method must not be private or static and must not return a value. Annotation test methods may optionally declare parameters to be resolved by parameter resolvers, and annotation test may be used as a meta annotation in order to create a custom composed annotation that inherits the semantics of ampersand test. This is in the module org.junit.jupyter.api and package org.junit.jupyter.api. As an example 3, we can consider extension model. For example, to register a web service extension, for a particular test method, you would annotate the test method as follows here. We assume the web server extension starts a local web server and injects the server's URL into parameters annotated with ampersand web server URL. Annotation interface extend with ampersand extend with is a repeatable annotation that is used to register extension for the annotated test class, test interface, test method, parameter or field. Here you can use web client to connect to web server and verify response. Here assert equals assert that expected and actuals are equal. This is expected and this is actual. As an example 4, we can consider this Gradle example. Here you can see the artifact ID JUnit Jupyter API. This is in the group org.junit.jupyter. As an example 5, we can consider this Maven segment. You can see the artifact ID JUnit Jupyter API here. This is in the group org.junit.jupyter. Here the version 5.8.2 and scope is test. As an example 6, we are now considering writing tests. Here the annotation interface at test is at test in package org.junit.jupyter.api in module org.junit.jupyter.api. At test is used to signal that the annotated method is a test method. The following example provides a glimpse at the minimum requirement for writing a test in JUnit Jupyter. Now we are considering metadata annotations and composed annotations. In annotations, at fast can then be used as a drop-in replacement for at tag fast. JUnit Jupyter annotations can be used as meta annotations. That means that you can define your own composed annotation that will automatically inherit the semantics of its meta annotations. For example, instead of copying and pasting at tag fast throughout your code base, you can create a custom composed annotation named at fast as follows. So at fast can then be used as a drop-in replacement for at tag fast. The following test method demonstrate the usage of at fast annotation. You can even take that one step further by introducing a custom fast tag annotation, at fast tag annotation that can be used as a drop-in replacement for at tag fast and at test, JUnit automatically recognizes the following as at test method that is tagged with fast. Now we are considering a standard test class in test classes and methods. Annotation interface test in package org.junit.jupyter.api in module org.junit.jupyter.api. At test is used to signal that the annotated method is a test method. The test methods and lifecycle methods may be declared locally within the current test class, inherited from superclasses or inherited from interfaces. In addition, test method and lifecycle method must not be abstract and must not return a value except at test factory methods which are required to return a value. Class and method visibility. Test classes, test methods, and lifecycle methods are not required to be public, but they must not be private. It is generally recommended to omit the public modifier for test classes and test methods and lifecycle methods unless there is a technical reason for doing so. For example, when a test class is extended by a test class in another package, another technical reason for making public class and public class and public classes and another technical reason for making classes and methods public is to simplify testing on a module path when using Java module system. The following test class demonstrate the usage of at test methods and all supported lifecycle methods. Not executed. Now we are considering display names. Test classes and test methods can declare custom display names via at display name with spaces and special characters and even emojis that will be displayed in test reports and by test runners and IDEs. The annotation interface display name in package org.junit.jupyter.api in module org.junit.jupyter.api. At display name is used to declare a custom display name for the annotated test class or test method. Here we are considering assertions. All JUnit assertions are static methods in the org.junit.jupyter.api.assertions class. The class assertions in package org.jupyter.api, in module org.jupyter.api. Assertions is a collection of fully utility methods that support asserting conditions in tests. JUnit Jupyter comes with the many assertion methods that JUnit 4 has, and adds a few that lend themselves to being used with Java 8 lambdas. All JUnit Jupyter assertions are static methods in the org.junit.jupyter.api.assertions class. Preemptive timeout with assert timeout preemptively. The various assert timeout preemptively methods in the assert class execute the provided executable or supplier in a different thread than that of the calling code. This behavior can lead to undesirable side effects if the code that is executed within the executable or supplier relies on jar.lang thread local storage. One common example of this is the transactional testing support in the Spring framework. Specifically, Spring's testing support bind transaction state to the current thread via a local thread before a test method is invoked. Consequently, if an executable or supplier provided to assert timeout preemptively invokes Spring managed component that participate in transactions, in any actions taken by those components will not be rolled back with the test managed transaction. On the contrary, such action will be committed to persistent store. For example, relational database, even though the test managed transaction is rolled back. Similar side effects may be encountered with other frameworks that rely on local thread storage. A group assertion, all assertions are executed and all failures will be reported together. Within a code block, if an assertion fails, subsequent code in the same block will be skipped. Execute only if the previous assertion is valid. Grouped assertion processed independently of the result of the first name assertions. Executed only if the previous assertion is valid. The following assertion succeeds. Perform task that takes less than 2 minutes. The following assertion succeeds and returns the supplied object. The following assertion invokes a method reference and returns an object. The following assertion fails and with an error message similar to exceeded timeout of 10 millisecond by 91 milliseconds. Simulate the task that takes more than 10 milliseconds. The following assertion will fails with an error message similar to execution timeout after 10 milliseconds. Simulate the task that takes more than 10 milliseconds. Here you can see the Kotling assertion support. All JUnit Jupyter Kotling assertions are top-level functions in the org.junit.jupyter.api package. JUnit Jupyter also comes with a few assertion methods that lend themselves well to being used in Kotling. All JUnit Jupyter Kotling assertions are top-level functions in the org.junit.jupyter.api package. This mapping returns a stream in JUnit. The following assertion fails with an error message similar to execution timeout after 10 milliseconds. Simulate the task that takes more than 10 milliseconds. Now we are considering assumptions. All Jupyter assumptions are static methods in the org.junit.jupyter.api.assumptions class. The class assumptions in package org.junit.jupyter.api in module org.junit.jupyter.api. Assumptions is a collection of utility methods that supports conditional test execution based on assumptions. JUnit Jupyter comes with a subset of assumption methods that JUnit 4 provides and adds a few that lend themselves well to being used with Java 8 Lambda expressions and method references. All JUnit Jupyter assumptions are static methods in the org.JUnit-Jupyter.api.assumptions class. As of Jupyter 5.4, it is also possible to use methods from JUnit 4's org.JUnit-assume class for assumptions. Specifically, JUnit Jupyter supports JUnit 4's assumption violated exception to signal that a test should be aborted instead of making as a failure. Reminder of test. Reminder of test. Perform these assertions only on CI server. Perform these assertions in all environments. Now we are considering disabling test. The entire class or individual test methods may be disabled via the @disabled annotation. Via one of the annotation annotation interface disabled in package org.JUnit-Jupyter.api in module org.JUnit-Jupyter.api. @disabled is used to signal that the annotated class or test method is currently disabled and should not be executed. Here is a @disabled test class. Here is a test class that contains a @disabled test method. @disabled may be declared without providing a reason. However, the JUnit team recommends that developers provide a short explanation for why a test class or a test method has been disabled. Consequently, these examples both show the use of a reason for example, here. Some development teams even require the presence of issue tracking numbers in the reason for automated traceability, etc. Now we are considering conditional test. Considering operating system and architecture conditions in conditional test execution. In the conditional execution based on operating system, the annotation interface enabled on OS in package org.JUnit-Jupyter.api.condition in module org.JUnit-Jupyter.api. @enabled on OS is used to signal that the annotated test class or test method is only enabled on one or more specified operating systems, or one or more specified architectures. The annotation interface disabled on OS in package org.junit.jupyter.api.condition in module org.junit.jupyter.api. At disable on OS is used to signal that the annotated test class or test method is disabled on one or more specified operating systems or more specified architectures. A container or test may be enabled or disabled on particular operating system architecture or combination of both via enabled OS and at disabled OS annotations. Here the conditional execution based on operating systems. Here the conditional execution based on architecture. Now we are considering tagging and filtering. Those tags can later be used to filter test discovery and execution. The annotation interface tag in package org.junit.jupyter.api in module org.junit.jupyter.api. Add tag is a repeatable annotation that is used to declare a tag for annotated test class or test method. Test classes and methods can be tagged via tag annotation. Those tags can later be used to filter test discovery and execution. Now we are considering method order in test execution order. The following example demonstrates how to guarantee that the test methods are executed in the order specified via the at order annotation. Annotation interface order in package org.junit.jupyter.api in module org.junit.jupyter.api. At order is an annotation that is used to configure the order in which the annotation element, that is field, method or class, should be evaluated or executed relative to the other elements in the same category. Although true unit tests typically should not rely on the order in which they are executed, there are times when it is necessary to enforce a specific test method execution order. For example, when writing integration test or functional test, where the sequence of test is important, especially in conjunction with at test instance the lifecycle.per chart per class. To control the order in which test methods are executed, annotate your test class or test interface with at test method order and specify the desired method order, or use one of the following built-in method order implementation. Method order dot display name, short test methods alpha numerically based on their display names. method orderer dot method name. Short test methods alphanumerically based on their names and formal parameter list. Method orderer dot order annotation. Short test method numerically based on the value specified via at order annotation. Method orderer random. Orders test method pseudo randomly and support configuration of custom seed. Method orderer dot alphanumeric. Short test methods alphanumerically based on the names and parameter list. Deprecated in favor of method order dot method name to be removed in 6.0. The following example demonstrates how to guarantee that test methods are executed in the order specified via at order annotation. Perform assertions against null values. Perform assertions against empty values. Perform assertions against valid values. Now we are considering changing the default test instance lifecycle in test instance lifecycle. For example, to set the default test instance lifecycle mode to lifecycle.per class, you can start your JVM with the following system property. If a test class or test interface is not annotated with at test instance, JUnit Jupyter will use default lifecycle mode. The standard default mode is per method. However, it is possible to change the default for the execution of an entire test plan. To change the default test instance lifecycle mode, set JUnit Jupyter.instance. Lifecycle.default configuration parameter to the name of an enum constants defined in the test instance lifecycle. Ignoring case, this can be supplied as a JVM system property as a configuration parameter in the launcher discovery request that is passed to the launcher or via the JUnit platform configuration file. For example, to set the default test instance lifecycle mode lifecycle.per class, you can start your JVM with the following system property here. Note, however, that the settings, the default test instance lifecycle mode via the JUnit platform configuration file is more robust solution, since configuration file can be checked into a version control system along with the project and can therefore be used within IDEs and your build software. To set the default test instance lifecycle mode to lifecycle.per class via the JUnit platform configuration file, create a file named JUnit-platform.properties in the root of the class path. For example, source, then test, then resources with the following content here. Changing the default test instance lifecycle mode can lead to unpredictable results and fragile builds if not applied consistently. For example, if the build configures a per class semantics as the default but the test in the IDE are executed using per method semantics, that can make the difficult to debug errors and that occur on the build servers. It is therefore recommended to change the default in the JUnit platform configuration file instead of via a JVM system property. Now we are considering nested test. Here is an elaborate example both as source code and as a screenshot of the execution within an IDE. The annotation interface nested in package org.junit.jupyter.api in module org.junit.jupyter.api At nested is used to signal that the annotated class is a nested non-static test class, that is an inner class that can share the setup and state with an instance of its enclosing class. The enclosing class may be a top level test class or another at nested test class, and nesting can be arbitrarily deep. At nested test give the test writer more capabilities to express the relationship among several groups of tests. Such nested tests make use of Java nested classes and facilitate hierarchical thinking about the test structure. Here's an elaborate example, both as a source code and as a screenshot of the execution of IDE. Within an IDE, here's the nested test suite for testing a stack. When executing this example in an IDE, the test execution tree in the GUI will look similar to the following image here. This is executing a nested test in an IDE. In this example, preconditions from the outer tests are used in the inner test by defining hierarchical lifecycle method for setup code. For example, create new stack. Method is before each lifecycle method that is used in the test class in which it is defined, and in all levels in the nesting tree below the class in which is defined, the fact that setup code from the outer tests is run before inner tests are executed gives you the ability to run all tests independently. You can even run inner test alone without running the outer test, because the setup code from the outer test is always executed. Only non-static nested classes, that is inner classes, can serve as at nested test classes. Nesting can be arbitrarily deep, and those inner classes are subject to full life cycle support with one exception. At before all, and after all methods do not work by default. The reason is that the Java does not allow static members in inner classes prior to Java 16. However, this restriction can be circumvented by annotating a nested test class with at test instance lifecycle.per class. If you are using Java 16 or higher, at before all and after all method can be declared as static at nested test class, and this restriction is this restriction no longer applies. Now we are considering test info parameter resolver in dependency injection for constructors and methods. The following demonstrates how to have a test info injected into a test constructor and at before each method and test method. Class testing for parameter resolver in package org.junit.jupyter.engine.exec extension. The parameter resolver that resolves the testing for the currently executing test. Testing for parameter resolver, if a constructor or method parameter of type testinfo, the testinfo parameter resolver will supply an instance of testinfo correspond to the current container or test. As a value for the parameter. The test info can then be used to retrieve information about current container or test such as display name, test class, test method, and associated tags. The display name is either technical name such as the name of the test class, so test method, or custom name configured via display name. The test info acts as a drop-in replacement for the test name rule from JUnit 4. The following demonstrate how to use how to have test info injected into test constructor before each method and at test method. Now we are considering test interfaces and default methods. Here are some examples. Jupyter allows at test at repeat test, at parameterized test, at text factory, at test template, and at before all, at before each, at after each, and after each to be declared on interface default methods. Before all, at before all, and at after at before all and at after all can either declared as static method in a test interface, so or on interface default methods if the test interface or test class is annotated with at test instance lifecycle dot per class. Here are some examples. At extend width and at tag can be declared on test interface so that classes that implement the interface automatically inherit its tags and extensions. In your class, you can then implement these test interfaces to have them applied. Running test interface demo results in the output similar to the following. Now we are considering repeated test, executing repeated test demo with the info log level enabled. Enabled result in the following output here. The annotation interface repeated test in package org.junit.jupyter.api in module org.junit.jupyter.api. At repeated test is used to signal that the annotated method is a test template method that should be repeated in a specified number of times with the configurable display name and optional failure. The failure threshold. A repeated test demo class at the here the demonstrates several examples of repeated test. The repeated test method is identical to the whereas the repeated test with repetition info. Here the demonstrate this sorry the repeated test method is you can see here, and whereas the repeated test with repetition info demonstrate how to have instance of repetition info injected into the test to access the total number of repetition for the current repeated test. Repeated test with failure threshold demonstrate how to start a failure threshold and simulate an unexpected failure for every second repetition. The resulting behavior can be reviewed in the console launch output at the end here, and the next two methods demonstrate how to include the custom at display name for at repeated test method in the display name of each repetition. The custom display name combines the custom display name with the custom pattern that uses test info to verify the format of the generated display name. Repeat bank sign is the display name which comes from the at display name declaration. One divided by 1 comes from the current repetition divided by total repetition. In contrast, the custom display name with the long pattern uses after mentioned predefined repeated test dot long display name pattern. Repeated test in German demonstrate the ability to translate the display names of repeated test into foreign languages. In this case German, resulting in names for individual repetitions such as Wiederholung, Wiederholung 115, Wiederholung 215, 5, etc. Since each before each since the before each method is annotated with at before each, it will execute before each repetition of each repeated test. We see that it's possible to obtain information about the current execution repeated test executing repeated test demo with info log level. Enable result in the following output here. When using the console launcher with the Unicode theme enabled, execution of repeated test demo result in the following output console here. Likewise, this goes to 10 repetitions. Simulate unexpected failure every second repetition. Likewise, this goes to up to repetition 10 of 10. Let's move to this one here. Then it comes to here, boom. Then here again, boom, and then threshold exceeded here. And the German repeated test in German is repeated 5 times. Likewise. Now we are considering parameterized tests. The following example demonstrates a parameterized test that uses at value source annotation to specify string array as a source of arguments. The annotation interface parameterized test in package org.jupyter.params in module org.jupyter.params. At parameterized test is used to signal that the annotated method is a parameterized test method. The parameterized test make it possible to run a test multiple times with the different arguments. If they are declared just like regular at test method, but use at parameterized test annotation instead. In addition, you must declare at least one source that will provide the argument for each invocation, then consume argument in test method. The following example demonstrate a parameterized test that uses value source. At value source annotation to specify string array of source arguments. When executing this parameterized test method, each invocation will be reported separately. For instance, console launcher will print out similar to the following. Test templates. Now we are considering test templates. A test template method is not a regular test case, but rather a template for test cases. The annotation interface test template in package org.jupyter.api in module org.jupyter.api. At test template is used to signal that the annotated method is a test template method. At test template method is not a regular test case but rather a template for test cases. As such, it is designed to be invoked multiple times depending on a number of invocation contexts returned by the registered providers. Thus, it must be used in conjunction with a registered test template invocation context provider extension. Each method invocation of a template method behave like the execution of the regular test method with full support for the same lifecycle callbacks and extensions. Repeated test and parameter test are built-in specializations of test templates. Now we are considering dynamic tests. For demonstration purposes, the dynamic not single test method generates a single dynamic test instead of a stream, and dynamic not single container method generate a nested hierarchy of dynamic tests utilizing dynamic container. The class dynamic test in package org.junit.jupyter.api in module org.junit.jupyter.api, a dynamic test is a test case generated at runtime. The following dynamic test demo class demonstrate the several examples of test factories and dynamic tests. The first test method returns invalid return type. Since an invalid type cannot be detected at compile time, JUnit exception is thrown when it is detected at runtime. The next 6 methods demonstrate the generation of collection and iterable and iterator and array and stream of dynamic test instances. Most of these examples do not really exhibit dynamic behavior but merely demonstrate the supported return type in principle. However, the dynamic test from stream and dynamic test from int stream demonstrate how to generate dynamic test for a given set of strings or range of input numbers. Next method is truly dynamic in nature. The generate random number of tests. Is of course next method is the the next method is truly dynamic in nature that generates random number of tests, implements an iterator that generates random numbers. A display name generator and Um, and a test executor, and then provides all three dynamic test.stream. Although non-deterministic behavior of generate random number tests is of course in conflict with the test repeatability and should thus be used with care, it serves to demonstrate the expressiveness and power of dynamic tests. The next method is similar to generate random number of tests in more flexibility. However, dynamic test from stream factory method generates a stream of dynamic test from existing stream via dynamic test.stream. Dynamic test.stream method, stream factory method. For demonstration purposes, dynamic not single test method generates a single dynamic test instead of a stream, and the dynamic not single container method generates a nested hierarchy of dynamic tests utilizing dynamic container. This will result a JUnit exception. Generate test for the first 10 even integers. Generates random positive integers between 1 and 100 until a number currently divisible by 7 encountered. Generate display names like input 5 input, 37 input, 85, etc. Execute test based on the current input value. Returns the stream of dynamic tests. Stream of palindromes to check. Generate display names like race car in the palindrome. Execute test based on the current input value. Return the stream of dynamic tests. Stream of palindromes to check. Return the stream of dynamic tests. Now we are considering timeouts. The following example shows how a timeout is applied to lifecycle and test methods. A timeout annotation allows one to declare that a test of a test factor, a test template, or lifecycle method should fail if its execution time exceeds the given duration. The time unit for the duration default to seconds, but it's configurable. The following example shows how a timeout is applied to lifecycle and test methods. To apply the same timeout to all test methods within a test class, all of its nested classes, and all of its nested classes, you can declare a timeout annotation at the class level. It will then be applied to all test factory, test template methods within that class, and it's at nested class unless overridden by a timeout. Annotations declared at the class level timeout annotation on the specific method or nested class. Please note that the timeout annotation declared at the class level are not applied to the lifecycle methods. Declaring a timeout at test factory method checks that factory method returns within a specified duration but does not verify the execution time of each individual dynamic test generated by the factory. Please use assert timeout method or assert timeout preemptively method for that purpose. If the timeout is present on at test template method, for example at repeated test or at parameters test, each invocation will have the given timeout applied to it. Fail if the execution time exceeds 5 seconds. Fail if the execution time exceeds 500 milliseconds. Fail if the execution time exceeds 500 millisecond. The test code is executed in a separate thread. Now we are considering parallel execution. Synchronization in parallel execution. Two tests that require read access. The two tests that require read access to a shared resource may run in parallel with each other, but not while any other test that required read-write access to the same shared resource is running. Annotation interface execution in package org.junit.jupyter.api.parallel in module org.junit.jupyter.api. At execution is used to configure the parallel execution mode of a test class or test method. Enum public static final execution mode concurrent. Enum class execution mode in package org.junit.jupyter.api.parallel in module org.junit.jupyter.api. Allow concurrent execution with any other node. In addition to controlling the execution mode using at execution annotation, JUnit Jupyter provides another annotation based declarative synchronization mechanism. At resource lock, annotation allows you to declare that a test class or method uses a specific shared resource that requires synchronized access to ensure reliable test execution. The shared resource is identified by a unique name, which is string. The name can be user defined or one of the predefined constant in resources, system properties, system out, system error, local or time zone. If the test in the following in example were run in parallel without the use of at resource lock, they would be flaky. Sometimes they would pass, and at other times they would fail due to inherent race condition of writing and then reading the same JVM system property. When access to shared resources is declared using at resource lock annotation, the JUnit Jupyter engine uses this information to ensure that no conflicting tests are run in parallel. Running tests in isolation, most of your test classes can be run in parallel without any synchronization, but you have some test classes that need to run in isolation. You can mark the latter with the at isolated annotation. Tests in such classes are executed sequentially without any other results, other tests running at the same time. In addition to the string that uniquely identifies the shared resource, you may specify an access mode. Two tests that require read access to a shared resource may run in parallel with each other, but not while any other test that requires read-write access to the same shared resource is running. Now we are considering the temp directory extension in built-in extensions, a test method that require a temporary directory. The annotation interface temp dir in package org.jupyter.api.io in module org.jupyter.api. At temp dir can be used to annotate a field in a test class, so a parameter in a lifecycle method or test method of type path or file that should be resolved into temporary directory. The built-in temp directory extension is used to create a cleanup temporary directory for individual test or all tests that in test class. It is registered by default. To use it, annotate a non-final unassigned field of type java.nio.file.path or java.io.file with at temp dir, or add a parameter of type java.nio.file.path or java.io.file annotated with at temp dir to a lifecycle method or test method. For example, the following test declared a parameter annotated with at temp dir for a single test method creates and write to a file in the temporary directory. And checks its contents. Now we are considering extension API, the overview. In contrast to the competing runner, test rule and method rule extension point in JUnit 4.0, sorry, for JUnit 4, the JUnit Jupyter extension model consists of a single coherent concept, the extension API. Note, however, that the extension itself is just a marker interface. Now we are considering declarative extension registration in registering extensions. We assume the web service extension starts a local web server and injects the server URL into parameter annotated with at web server URL. The annotation interface extend with in package org.junit.jupyter.api.extension in module org.junit.jupyter.api. At extension with is a repeatable annotation that is used to register extension for annotated test class, test interface, test method, parameter, or field. Developers can register one or more extension declaratively by annotating a test interface, test class, test method, or custom composed annotation with at extend with, and supplying the class references for extension to register. As of JUnit Jupyter 5.8, the extend with at extend with may also be declared on fields or on parameters in test class constructor, in test methods, and in at before, at after all, at before, at after all, at before each, and at after each lifecycle methods. For example, to register web server extension for a particular test method, you would annotate the test method as follows. We assume the web server extension starts a local web server and injects the server's URL into parameters annotated with at web server URL. To register the web server, web server extension for all tests in particular class and its subclasses, you would annotate the test class as follows. Multiple extensions can be registered together like this. As an alternative, multiple extensions can be registered separately like this. Extensions registered declarative at extend with at class level, method level, or parameter level will be executed in the order in which they are declared in the source code. For example, the execution test in both my first tests and my second test will be extended by the database extension and web server extension in exactly that order. Use the web client to connect to the web server using server URL and verify the response. Now we are considering deactivating conditions in conditional test execution. For example, to deactivate JUnits at disabled condition, you can start your JVM with the following system property. Sometimes it can be useful to run the test suite without certain conditions being active. For example, you may wish to run test even if they are annotated with a disabled in order to see if they are still broken. To do this, provide a pattern for JUnit.condition.deactivate configuration parameter to specify which condition should be deactivated that is not evaluated for the current test run. The pattern can be supplied as a JVM property as a configuration parameter launcher discovery request that is passed to the launcher or via the JUnit platform configuration file. For example, to deactivate the JUnit at disabled condition, you can start your JVM with the following system property. Now we are considering test instance pre-construct callback. Test instance pre-construct callback define the API for extension that wish to be invoked prior to the test instances being constructed by a constructor call or via test instance factory. Interface test instance pre-construct callback in package org.junit.jupyter.api.extension in module org.junit.jupyter.api. Test instance pre-construct callback define the API for extension that wish to be invoked prior to the creation of test instances. This extension provides a symmetric call to test instance pre-destroy callback and is useful in combination with other extensions to prepare constructor parameters, so keeping track of test instances and their life cycle. Now we are considering test instance factories. Test instance factory defines then the API for extension that wish to create test class instances. Interface test instance factory in package org.junit.jupyter.api.extension in module org.junit.jupyter.api. Test instance factory define API for extension that wish to create test instances. Common use cases include acquiring a test instance from a dependency injection framework or invoking study factory method to create a test class instance. If no test instance factory registered, the framework will invoke the sole constructor for the test class to instantiate it, potentially resolving construct argument via registered parameter resolver extensions. Extensions that implement test instance factory can be registered on the test interface's top level test class, so nested test classes. Registering multiple extensions that implement a test instance factory or for any single class will result exception being thrown for all tests that in that class in any subclasses and in nested classes. Note that test instance factory registered in a superclass or enclosing class, that is the case of at nested class, is inherited. It is a user's responsibility to ensure that only a single test factory test instance factory registered for any specific test class. Test instance post-processing. Test instance post-processor defines the API for extensions that wish to post-process test instances. Interface test instance post-processor in package org.junit.jupyter.api.extension in module org.junit.jupyter.api. Test instance post-processor defines the API for extensions that wish to post-process test instances. Common use case include injecting dependencies into the test instance, invoking custom initialization methods on the test instance, etc. For a concrete example, consult your source code for mock2 extension and the extension examples in documentation. Test instance pre-destroy callback. Test instance pre-destroy callback define the API for extensions that wish to process test instances after they have been used in test and before they are destroyed. Interface test instance pre-destroy callback in package org.junit.jupyter.api.extension in module org.junit.jupyter.api. Test instance pre-destroy callback defines the API for extension that wish to process test instances after they have been used in test but before they are destroyed. Common use cases include cleaning the dependencies that have been injected into the test instance, invoking custom initialization methods on the test instance, etc. Parameter resolution. Parameter resolver defines the extension API for dynamically resolving parameters at runtime. Interface parameter resolver in package log to JUnit.API.extension in module log to JUnit.API. Parameter resolver that defines the API for extensions that wish to dynamically resolve argument for parameters at runtime. If a test class constructs a test method or lifecycle method declares a parameter, the parameter must be resolved at runtime by a parameter resolver. Parameter resolver can either be built in or registered by the user. Generically speaking, parameters may be resolved by name, type, annotation, or any combination thereof. If you wish to implement a custom parameter resolver that resolves the parameter based solely on the type of the parameter, you may find convenient to extend the type-based parameter resolver, which serves as a generic adapter for this for such use cases. Due to the bug in bytecode generated by Java C on JDK versions 5 to JDK 9, looking up the annotation in parameter directly via the core java.lang.reflector parameter API always fail for inner class constructor, that is a constructor in a nested test class. The parameter context API supplied to the parameter resolver implementation therefore include the following convenient method for correctly looking up the annotations on parameters. Extensions authors are strongly encouraged to use these methods instead of those provided in java.lang.reflector parameter in order to avoid this bug in the JDK. Boolean is annotated, classed question mark extended annotation type, optional A find annotation, class A annotation type, list A find repeatable annotations, class A annotation type. The other extensions can also leverage registered parameter resolvers for method and constructor invocations using executable invoker available via the get executable invoker method in the extensions context. Test result processing. Watcher defines the API for extensions that wish to process the result of the test method execution. Specifically, a test watcher will be invoked in contextual information for the following for the events. Interface test watcher in package log.jupyter.api.extension in module log.jupyter.api. Test watcher defines the API for extensions that wish to process test results. Test disabled invoked after disabled test method has been skipped. Test successful invoked after test method has completed successfully. Test aborted invoked after test method has been aborted. Test failed invoked after a test method failed. In constructs to the definition of a test method presented in definitions, in this context, test method refer to any at test method or at test template method. For example, at repeated test or at parameterized test. Extensions implemented in this interface can be registered at the class level, instance level, or method level. When registered at the class level, a test watcher must invoked for any contained test method, including those in the nested classes. When registered at the method level, a test watcher will only be invoked for the test method for which it was registered. If a test watcher is registered via an unstatic instance field, for example, at registration extension, the test class is configured with at instance lifecycle.per method semantics, which is default lifecycle mode, the test watcher will not be invoked with events for at template test methods, for example, at repeated test or at parameterized test. To ensure the test watcher is invoked to all test methods in a given class, it is therefore recommended that the test watcher is to be registered at the class level with at extension with or via static field with at registration as register extensions or extends with. If there is a failure at the class level, for example, exception thrown by at before all method, no test result will be reported. Similarly, if the test class is disabled via an execution condition, for example, at disabled, no test result will be reported. In contrast to the other extension in APIs, the test watcher is not permitted to adversely influence the execution of tests. Consequently, any exception thrown at the method in the test watcher API will be logged at warning level and will not be allowed to propagate or fail test execution. In instances of extension context.store.closable resource stored in the store of the provided extension context will be closed before methods in the test watcher API are invoked, you can use the parent context store to work with such resources. Now we are considering before and after test execution callbacks in test lifecycle callbacks, an extension that times and logs the execution test methods. The interface before test execution callback in package org.jupyter.api.extension in module org.jupyter.api. The before test execution callback define API for extensions that wish to provide additional behavior to test immediately before an individual test is executed, but after any user defined set of methods. That is, for example, at before each methods have been executed for that test. Interface after test execution callback in package org.jupyter.api.extension in module org.jupyter.api. After test execution callback define API for extension that wish to provide additional behavior to test immediately after the individual test has been executed, but after any user defined set of methods, for example, after each before any user defined setup methods, for example, at after each methods have been executed for that test. Before test execution callback and after test execution callbacks define the API for extension that wish to add the behavior that will be executed immediately before and immediately after. A test method is executed respectively. As such, these callbacks are well suited for timing and tracing and similar use cases. If you need to implement a callback that are invoked around at before and after after each methods, implement before each callback and after each callback instead. Following example shows how to use these callbacks to calculate and log the execution time of a test method. The time extension implements both before test execution callback and after test execution callback in order to time and log the test execution. Since timing extension tests class registered the timing extension via at extend with its test will have the timing applied when they execute. The following is an example of logging produced when timing extension class extension test is run. It's the get store method. I just missed it. Now we are considering exception handling, and exception handling extension that filters the IO exception in test execution. The interface test execution exception handler in package jog.jnut.api.extension in module jog.jnut.api. The test execution exception handler defines the API for extension that wish to handle exceptions thrown during test execution. Exceptions thrown during the test execution may be intercepted and handled accordingly before propagating further, and so certain actions like error logging or resource releasing may be defined in specialized extensions. JUnit Jupyter offers API for extensions that wish to handle exceptions thrown during a test method via test execution exception handler, or for those thrown during one of the test lifecycle method, at before all, at each, at before each, at after each, and at after all via lifecycle method execution exception handler. The following example shows the extension that wish swallow all instances of IO exception, but rethrow any other exception type. Now we are considering an intercepting invocations, an extension that execute test in a user-defined thread. The interface invocation interceptor in package org.jnut.api.extension in module org.jnut.api. Invocation interceptor defines the API for extension that wish to intercept calls to test code, to the test code. Invocation interceptor defines the API for extension that wish to intercept calls to the test code. The following example shows the extension that execute all test methods at swings event dispatch thread. At test and template, now we are considering provide invocation context for test templates. A test template will accompanying extension. The interface test template invocation provider in package org.jnut.api.extension in module org.jnut.api. A test template invocation context provider defines the API for extension that wish to provide one or more multiple contexts for the invocation of a test template method. A test template method can only be executed when at least one test template invocation context provider is registered. Each such provider is responsible for providing a stream of test template invocation context. context instances. Each context may specify custom display name and list of additional extensions that will only be used for the next invocation of a test template method. The following example shows how to write a test template as well as how to register and implement test template invocation context provider. In this example, the test template will be invoked twice. The display names of the invocation will be apple and banana as is specified by the invocation context. Each invocation registers a custom parameter resolver which uses to resolve the method parameter output when using the console launcher as follows. The test template invocation context provider extension API is primarily intended for implementing different kind of tests that rely on repetitive invocation of tests like method, albeit in different context. For example, with different parameters by preparing the context class instances differently or multiple times without modifying the context. Please refer the implementation of repeated test and parameter test, which use the extension point to provide their functionality. Now we are considering keeping state in extensions. Consult the corresponding Java doc for details on the methods available for storing and retrieving values via the store. Interface extension context.store in package org.junit.api.extension in module org.junit.api. The store provides the method for extensions to save and retrieve data. Usually an extension is initiated by only once. So the question becomes relevant, how do you keep the state of the one instances of an extension to the next? The extension context API provides store exactly for the purpose. Extension may put values into a store later for a later retrieval. It is important to remember that values stored in the extension context during the test execution will not be available in the surrounding extension context. Since the extension context may be nested, the scope of inner context may be also be limited. Consult the corresponding Java doc for details on the methods available for storing and retrieving via store. Extension context.store.closable resource. An extension context store is bound to its extension context lifecycle. When an extension context lifecycle ends, it closes its associated store. All stored values that are instances of closable resource are not notified by an invocation of their close method. in the inverse order they were added in. Now we are considering annotation support in supported utilities in extensions. Consult the Java doc for annotation support for further details. Class annotation support in package org.jmd.platform.commons.support in module org.jmd. In the module org.platform.commons, this is basically with the platform. The annotation support provides static utility methods for common tasks regarding annotation. For example, checking if a class method or field is annotated with a particular annotation, finding annotation on a given class method or field, finding fields so methods annotated with a particular annotation. So this is more related to generic platform. Annotation support provides static utility methods that operate on annotation elements, packages, annotations, classes, interfaces, constructors, methods, and fields. These include methods to check whether an element is annotated or meta annotated with a particular annotation, to search for specific annotations, and to find annotated method and the fields in the class or interface. Some of these methods search on implemented interface and within class hierarchies to find annotations. Now we are considering relative execution order of use code and extensions. Here, wrapping behavior of callbacks. All methods imported statistically from a logger class log contextual information in order to help us better understanding of the execution order of the user applied callback and callback methods in extensions. Before each callback in package org.jupyter.api.extension in module org.jupyter.api. The before each callback defines the API for extension that wish to provide additional behavior to test before an individual test and any user-defined set of methods. For example, at before each methods for that test have been executed. Interface after each callback in package org.jupyter.api.extension in module org.jupyter.api. Each after each callback define the API for extension that wish to provide additional behavior to test after the individual test and any user-defined tear down methods. For example, after each methods for that have been executed. General Jupyter always guarantees the wrapping behavior of the multiple register extensions that implement the lifecycle callback, such as before all callback, after all callback. Before each callback, after each callback, before test execution callback, and after test execution callback. That means that the given two extension 1 and extension 2 with the extension 1 registered before extension 2, any before callback implemented by extension 1 are guaranteed to execute before callbacks implemented by extension 2. Similarly, given the two extension registered in the same order and any after callbacks implemented by extension 1 is guaranteed to execute after any after callbacks implemented by execution 2. Extension 1 and extension 2 therefore set to wrap extension 1 is therefore set to wrap extension 2. JUnit Jupyter also guarantees the wrapping behavior within class and interface hierarchies for user supplied lifecycle method. Before all, methods are inherited from the superclass as long as they are not hidden, overridden, or superseded, that is replaced based on the signature only, irrespective of Java visibility rules. Therefore, before all methods from the superclass will be executed before all methods in the subclass. Similarly, that before all methods declared in an interface are inherited as long as they are not hidden, overridden, and before all methods from the interface will be executed before all methods in the class that implement the interface. After all, methods are inherited from the superclass as long as they are not hidden, overridden, or superseded. That is replaced based on the signature only, irrespective of Java visibility rules. Therefore, after all methods from the superclass will be executed after all methods in the subclass. Similarly, after all method declared in the interfaces are inherited as long as they are not hidden or overridden, and after all methods from the interface will be executed after all methods in that class implements the interface. At before each methods are inherited from the superclass as long as they are not overridden or superseded. That is replaced based on the signatures only and irrespective of Java visibility rules. Therefore, at before each methods from the superclass will be executed before each methods in the subclass. Similarly, at before each methods declared as interface default methods are inherited as long as they are not overridden, and before each default method will be executed before each methods in this class implements the interface. After each methods are inherited from the superclass as long as they are not overridden or superseded, replaced based on the signature and irrespective of Java visibility rules. Therefore, furthermore, after each method from the superclass will be executed after each method in the subclass. Similarly, after each method declared as an interface, default methods are inherited as long as they are not overridden, and after each default method will be executed after each methods in the class that implements the interface. Following examples demonstrate that behavior. Please note that the example do not actually do anything realistic. Instead of mimic the common scenarios for testing interaction with the database. All methods important statistically for the logger class log contextual information in order to help us better understanding of the execution order of the supplied callback method and callback methods extensions. Now we are considering JUnit Jupyter in dependency metadata. The JUnit Jupyter API in artifact ID JUnit Jupyter API in group ID org.JUnit Jupyter. JUnit Jupyter API for writing tests and extensions. As an example, we can consider this quad segment. Here the method public static t extend throwable t assert throws class t expected value and executable here. Assert that execution of the supplied executable throws an exception of the expected type and returns the exception. If no exception is thrown, or if the exception is of a different type is thrown, this method will fail. If you do not want to perform additional checks on the exception instance, ignore the return value. This method is in class assertions. As an example, we can consider this error occurred in the environment JUnit and Maven project. This error occurred in JUnit and Maven project in NetBeans. Error package org.junit.jupyter.api does not exist. Now we are focusing on JUnit-Jupyter-engine. JUnit Jupyter test engine implementation only required at runtime. As an example, we can consider package org.junit.jupyter.engine core package for the JUnit Jupyter test engine is in module org.junit.jupyter.engine. As an example 2, we can consider default Jupyter configuration class, default implementation of the Jupyter configuration API. This is in the module org.junit.jupyter.engine and package org.junit.jupyter.engine.config. As an example 3, we can consider this code segment. Here you can see the class Jupyter test engine, the JUnit Jupyter test engine. Here you can see the method public test description discover here, engine discovery request and unique ID here. This method discovers test according to the supplied engine discovery request. This class is in module org.junit.jupyter.engine and package the org.junit.jupyter.engine. Here the supplied unique ID must be used as the unique ID of the returned root test descriptor. Here the engine discovery request provide the test engine access to the information necessary to discover test and containers. And the unique ID encapsulates the creation and passing and display unique IDs for test descriptors. The interface test descriptor, the mutable descriptor for a test or container that has been discovered by a test engine. Here you can see the Gradle segment for additional Gradle dependencies for IntelliJ IDEA. Here you can see artifact ID JUnit Jupyter Engine, module JUnit Jupyter Engine of JUnit 5, JUnit Jupyter test engine implementation only required at runtime here. This is in the group ID org.junit.jupyter. You can see this one, JUnit Jupyter Engine. As an example 5, we can consider this Maven segment for additional Gradle dependencies for IntelliJ IDEA. Here you can see artifact ID JUnit-Jupyter-engine, module JUnit Jupyter Engine of JUnit 5, JUnit Jupyter test engine implementation only required at runtime. This is in the group ID org.junit.jupyter. Now we are considering registering a test engine in test engines. For example, the JUnit Jupyter engine module register is org.junit.jupyter.test Jupyter test engine in a file named org.junit.platform.engine.test engine within the /meta-info/services folder in JUnit Jupyter engine jar. A test engine registration is supported via Java's service loader mechanism. Now we are considering JUnit Jupyter in dependency metadata. Artifact ID JUnit Jupyter engine in org.junit.jupyter. JUnit Jupyter test engine implementation only required at runtime. As an example, we can consider test execution exception handler, interface test execution exception handler. This is a functional interface and can therefore be used as the assignment target for a lambda expression or method reference. This is in the package org.junit.jupyter.api.extension.